Okay, so the graph y equals e to the 2x. Y equals e to the 2 times x power. You take a look at the graph in the standard viewing window. I don't think it's useful to do that at this point because we're only living in the world of really 0 to 1. It's saying the graphs of the function x equals 1 and the coordinate axes. So let's let the calculator do the window for us. So 0 to 1 for x min, x max. And I got to be in double digits now for the number of times I've showed this. So, but I'll make up a number. So for the 12th time, you go to y min or y max, it doesn't matter. Okay, clear, then zoom 0. 0. All right, and that's what we're looking at. Now, this is actually a good development here because sometimes the calculator is a little finicky, and you can see here that there's no x-axis, but I want the x-axis. The calculator finds what it thinks is the minimum value on an interval and what it thinks is the maximum value on that interval, and it builds the window around that. So when you see that, you have a y min of 1 rather than 0. Well, you don't have to be beholden to the calculator's final ruling here. The calculator's decreed that this must be the window. No, you could change it. All right. So I want to see the x-axis. So I'm going to make my y min equal to 0 and hit graph. All right. So ideally, you'd look at that and say, you know, that original graph, and say, wait a minute. That kind of exponential function wouldn't go through the origin. That just makes sense. It must be elevated. But the lack of a solid black line horizontal at the bottom, that's your real indicator. All right. So this is the interval that I'm spinning. I'm spinning it around the y-axis, and it's going. Well, I'll just label it up here. We have interval of 0 to 1 for x, and then an interval from obviously 0. But then on the high side, it's not going to be a clean number. This is the function y equals e to the 2x, e to the 2x. Any coordinate, again, as always, is x comma y. So in this case, the coordinate would have an x value of 1 and a y value of whatever the y value is when you plug a 1 into the function. So y equals e to the 2 times 1, so e squared. So not as nice a looking situation as the previous question, but we'll live with it. Now we're going to spin. We're going to spin it around the y-axis. All right, so you have a graph, and you know, this is the now what moment. Where if you're going to get stuck on a question like this, it's going to happen right here. Be like, now what? Now what do I do? So I have to spin all of this, with the yellow highlighter again, all of this area, all of this stuff around the y-axis. Now, if I could spin it around the x-axis, this would be a disk method problem, and it would be very easy. If I was spinning the other region, the part that I didn't shade around the y-axis, also disk method. Unfortunately, here we're stuck. We have to use the washer method, at least until I teach you about cylindrical shells. So, first off, we have a function here. The line x equals 1, just like the last question. That needs to get spun around. So I'm going to draw a skinny little rectangle down here. Oh, I missed. Kind of, I got some up. So skinny little rectangle shaded in, try to make it look halfway decent. That's got a distance, a thickness, sorry, of dy. All right. It has a length of x in terms of y. All right, so the question becomes, if I'm using the washer method, what would I subtract from that? Well, actually, it turns out that you're not at all points in this problem using the washer method. Because on the interval from 0 to 1, I can get where I want to go using the single arbitrary rectangle. So no matter where I place this rectangle on the interval of 0 to 1 here for y, I'm still going to cover this part. So that would be as if I spun this around using the disk method. All right, so that little bit there, it complicates, but it simplifies. All right, it complicates because it means that you have to take into account another aspect of the problem, but it's not an overwhelmingly challenging addition, so it's not bad. All right, so on the interval of 0 to 1, I'm going to have a pi r squared dy. And that r squared is x, and x is equal to 1 at all points on that interval. So I'm just going to put in a 1 dy. Now, if you visualize that, spin that region around, the whole region, just one chunk. You have a single chunk of area spun around. It would create a cylinder. So if you wanted to, you could avoid the integral part for this component and just use the volume of a cylinder formula, pi r squared h. All right, and you'll see that's actually how, that's one of the ways in which we can come up with the formula pi r squared h to find volumes of cylinders. One derivation of that comes from this idea. So it's kind of cool in that regard. Debating whether or not I want to show you that right now. I'll show it. Okay, so then on the interval, so going the rest of the way, from 1 to e squared, I'm gonna have washers. All right. So I'm looking at an arbitrary rectangle that would go, no matter where I place it, it's going to go all the way to 1. And have a thickness dy with a length of x. Alright, so a pi r squared dy. Now that r is the x, it's the x length of that rectangle, and that length itself is equal to 1. From that, I'm going to subtract the dimensions of my other arbitrary rectangle. Thickness dy, pi r squared dy, some length x equal to, well, it's related to this function, y equals e to the 2x. So I need to solve that for x in terms of y. So I have to use a natural log, or I have to convert over. It depends. Most people like to use the technique of finding the log of both sides, because then after that it's just properties. Because then the power rule for logs, exponent jumps over to log like a frog. The natural log of e is equal to 1, that cancels, and so we would get x being equal to 1/2 ln of y. So 1/2 ln y. And then from there, you could, again, run into the same, internal conversation where it's like, do I want to do this by hand or in the calculator? Again, haven't taught you how to find the antiderivative of natural log yet, so there goes that idea. If you already know how to do it, that's fine, but your calculator knows how to do it too. dy got cut off. There's a little dy at the end there. Try to see if I could scoot it over. And scooting accomplished. Okay, so to the calculator we go. All of that is the moral of the story. Go to the calculator. Don't forget you have a calculator. 0 to 1. Well, pi times 1 squared is really just pi. dy. Assuming you don't want to use the x button. Math 9, so plus math 9. 1 go into e squared. Pi 1 squared dy. Now, we can do all this in one shot, though. So instead of coming up with the function again, math 9, just type in these two guys. So we're going to think of this as pi minus pi times 1/2 ln y dy. So that's how I prefer to write it in. Type it in. Oops, squared. Point 5 ln y. The whole thing is squared. And that should do it. Y. And hopefully I typed that all in right. Guaranteed. See if it's some multiple of pi. Find out pi. Get that. Highly doubtful. Let's try the math bracket anyway. Yeah, it doesn't frac over. So it's probably some power of pi. Wait, I guess it's possible. But, or maybe it's close to some fractional decimal, but not close enough for the calculator to recognize it. So it is what it is. Let R be the region in the first quadrant enclosed by graphs of y equals meh and x equals 7 and the coordinate axes. Spinning it around the y-axis. Do it in the calculator again. All right, we're going out to 7, an x value of 7, so window 0 to 7, so for the 13th time, y min, clear, zoom, 0. And it'll give us our window. And again, calculator's lying to us. This graph has a y-intercept of 1. Definitely did not go through the origin. And you can see that it took us up to 1 for the y min. But it found the absolute minimum and the absolute maximum over that interval. Thought that's what we wanted, and that's what it gave us. And so it's a well-intentioned calculator, but sometimes it's not experienced enough, I guess. All right, spinning it around the y-axis. Definitely doable. All right, we're going from 0 to 7. This is the 1. This certainly looks like a 2. I don't know that we can just assume that, though, without at least verifying it in some way. And it will work out to be 2. But for your own purposes, you don't want to just take a guess. That's a disaster waiting to happen. Right? If I plug in a 7 here for x, 7 plus 1 is 8, 8 to the 1/3 power, so the cube root of 8 is 2. So that's where that comes from. All right. So this is very much like the previous question, where you have a whole chunk of interval going from 0 to 1 that's unrelated to the given function. It has some x value, some known x value, in this case x equals 7. And I can draw a single rectangle on that interval, and it's going to go from beginning of the bounded area to the end without any interruption. So that's a disk situation. Right, so I'm looking at, on the interval of 0 to 1, I'm looking at pi times the x value, which is 7. So pi times 7 squared dy. The other one is a little easier to see now because you can directly compare it to the one that we just did because its framework is identical. The graph looks slightly different, but it's similar enough that you say, oh, I'll just do what I did above. And that happens to be the case with a lot of these. That's good news. So I have my dy here. And then my other arbitrary rectangle, somewhere like this, also a dy has a thickness associated with that. All right. My green rectangle has a length of 7, x equals 7, so we're all set there. My blue one has an equation of x equals something, so I have to solve my given equation for x. So cube both sides, y cubed equals x plus 1. So we get, x equals, son of a gun, heck. Y cubed equals x plus 1. And then subtract the 1, we have y cubed minus 1 equals x. Alright, so x equals y cubed minus 1. So plus integral going from 1 to 2. We have a pi r squared, that r is a 7, dy. And then from that we subtract, also in the interval of 1 to 2, a pi times the other x squared. This time it's y cubed minus 1 dy. Alright, so it's really, I mean, in terms of the setup, essentially the same as the last one that we did. But, I mean, I don't feel a need to put it in the calculator. I don't need that payoff. It's pretty much the exact same thing we just did, so I'm going to leave it at that.